Okay, I think we should start today's lecture. So, we had this topic of the algorithms in which we discussed the techniques to find the complexity of different programs using the time and space complexity. So, moving forward in the same direction, we may be having the algorithms where the normal logic in which the complexity of the algorithm depends upon the size or the input parameter, that is n, is not valid all the time. So to clarify our point, we will firstly do some little bit mathematics, and after that we will return back to our presentation. Suppose we are having a function is given to us, f of n, and this function is like linear in time. So if we draw a graph for this type of function which is linear in nature, so this means that we can have a table here and we will be having some values of n. This is n. This is n1, 2, 4, 6, and the corresponding fn, as it is a function, means fn's value will depend on the value of the n. But since it is a linear type of function, whatever the value n will take, the fn will also take the same type of values. Okay, so if we draw it graphically here, so at 1 it will be 1, at 2 it will be 2, at 4 it will be like this, at 6 it will be like this. So we will get a linear line or a straight line which will connect to these different dots. Yes, but the scenario couldn't be like this. There could be a function which will be also dependent on the input size, but not linear in a quadratic way. Yes, this could be also the complexity of an algorithm, because whenever we are using a matrix addition type of function in which there are two loops, the external loop, and inside there is one more nested loop, that is from I is equal to 1 to n, and inside that for I loop there is one more loop for j is equal to 1 to n. So the complexity of the external loop will be n, and accordingly the complexity of the internal will be also n. N into n will be at that very time n square. That will be the algorithm of complexity of that algorithm. So if we take the same values here, 1, 2, 3, 4, 5, since the function is having a quadratic or a square relation with the n value, so whenever the value of 1 is equal to n is equal to 1, it will be 1. Whenever n is equal to 2, it will be the double. Whenever n is equal to 3, it will be 3 square. It will be like 16. It will be like 25. So as soon as the value of n increases, the corresponding value of the function also increases, but in a very high manner, quadratic manner. So if we draw the graph of this function also, so whenever n takes value 1, 2, 3, 4, and 5, the corresponding value, this is n in this very direction of this graph, and on this very direction, that is the vertical one, this is f of n, the corresponding values. So whenever fn n is equal to 1, the value of the fn is equal to 1 at that very time. This is the how they will be drawn on the graph. But as soon as the value of n is equal to 2, the value of fn won't be equal to 2 at that area. It will be equal to like 4 here. So we will go from n is equal to 2 and fn will be like 4. It will be here. So again, when we draw n is equal to 3, this value, the corresponding fn value at that time is 9. So it is 4, 5, 6, 7, 8, 9 is like here. Okay. So we will go from this side and we will see where the 9 lies. It will be like here. Okay. So accordingly, when we put the value n is equal to 4, the value of 16 will be like here. So we see that the function value varies like this. It's not a straight line, but it becomes like this sort of. Yes, because whenever we increase the value of n, the fn value increases in a very huge amount. So it will be like it is initially drawn like this, but then shifting towards left side, that's towards fn side. So this is the case in the quadratic. Now we will increase, we will now go to increase one more value to n and we will draw the cube. Okay. Again, we will take the same values and we will draw the graph directly without going into the table. So this will be n towards the horizontal side and the corresponding values towards the vertical side, fn. So whenever n is equal to 1, we will get 1 here also. So this will be its meeting point. When n is equal to 2, you see the value of fn at that time will be equal to 8. So the meeting point is like this. And when n is equal to 3, 3 into 3 into 3, that will be 27. Suppose 27 is something like here. So whenever we meet these points, it will be like this. So the point here is that as soon as the relationship between the input parameter size and the function gets increased, it gets shifted from linear to quadratic to cubic or to exponential. It could be fn could be sometimes also equal to 2 to the power n. This could be also the complexity of any algorithm. So the point is, from moving, initially the line was like this when the complexity was linear in time. The amount of n is increased, the fn also increases in the same way. When we increase, when the complexity got increased to n square, which means the quadratic, the graph came like this. But as soon as the complexity got to n cube, which we saw in this graph, the graph started from 1 to 1, then it increased to 8 and 27. So each time the complexity of the algorithm increases, the value of the corresponding fn gets very high in nature. Like in case of quadratic, when n was equal to 3, the value of square was equal to 3 square, that was 9. But here when it is n cube, it's 27. So when the value of n was equal to 3, fn at that very time when it was quadratic was 9. But when it was cubic, value of n is again 3. But fn at that very time became 27. You see, the value of fn increases in a very short period of time. And these type of functions, where the value increases in a very short period of time and the value increases in a very high manner, very scalable manner. Like initially it was 3, n was 3, fn was 3 if it is linear. N is 3, fn was 9 if it is quadratic. N is 3, fn is 27. So this abrupt increase in the value of fn, okay, this gives the graph like this figure. It moves towards the fn side. You see its arm gets shifted towards fn because the value of fn comes to be very high whenever the value of n changes. And there could be a point when the value of n, when the value of n increases. There could be a point when we increase the value of n, like initially it was 3, then 4, then 5, then 6. A value of n we will reach when the function value will go like infinity. You see? Okay. These type of functions where on increasing the value of n, the function value f of n increases in a very short period of time. These functions are known as asymptotic functions. Asymptotic functions. Okay. So you can give the definition in terms of mathematics. You can give the definition just by remembering that whenever we increase the value of one parameter, the corresponding value of the function gets increased in a very huge amount with a little period of time. These type of functions we call as asymptotic. And asymptotic functions are another way of measuring the complexity of the algorithm using the techniques like we will see here in the presentation. So what actually we are actually trying to find out here, we are having a function f of n. It is quadratic in nature. It is f of n is equal to 5n square plus 6n plus 12. Now we will substitute the values of n starting from 1, then increasing to 5, 6, 7, 8, 10, and then accordingly 100 and 1000, and we will see the corresponding values of fn. Okay, you see whenever we put n is equal to 1 in this very function f of 5n square plus 6n plus 12, so we will see that the first term, which is 5n square here, we will see how much computing time only this term will need, how much CPU running time it will need, only this term, because this expression is composed of three terms. So the 5n square, that is the quadratic term, when we put n is equal to 1, we will see the percentage of running time which is taken by 5n square. So as per the formula, it is simple that we will put 5 on the top, that's the numerator, and below we will see the total time taken by whole of the expression. The time taken by this quadratic expression divided by the total, that is 5 divided by 5 plus 6 plus 12. This thing. So whenever we perform this numerical experimentation and multiply it with 100 so as to convert into percentage, we will get it 21.74. This is, you can do by just using the paper and pencil. So here, now we will again find the total time or the total CPU time the next term of this expression will need to execute itself. So whenever we put n is equal to 1, and the percentage of running time which is needed by the 6n will be, again, that will be 6. I have not written it here, but that will be 6 divided by 5 plus 6 plus 12. Like on the first case, it was 5. So whenever we, after calculating the value of this term, it will be come out to be 26.9%. That is the CPU time for executing this whole equation will be divided into 3. The quadratic term, it will need 21.74, the linear term 26, and then there is the constant term. For constant term, we will again try to find the total execution time of the CPU this will need to get executed. Again, it will be 12 divided by 5 plus 6 plus 12. Okay. So whenever we also do this numerical calculation, the percentage will be 52.17. So for whole of this expression, which is divided into 3 different subtasks or sub terms, by seeing the total percentage of the CPU time, it comes to our mind that the quadratic term takes 21 of the CPU time. If it is 100 seconds, so it means it takes 21 seconds. The linear term takes 26 seconds and the constant term takes 52. So by looking on these results which we get, it seems like most of the time while evaluating this expression is taken in the constant term, that's 12. But this is not the case, because what we did, we took only the value of n is equal to 1. As we saw in the previous example which I wrote on the whiteboard, whenever we increase the value of n, we don't have to take any conclusion just by taking the value of n is equal to 1. So we will increase the value of n and we will see then the corresponding amount of the CPU taken by all the terms. So there is a table which I have drawn it here. I will share those PPTs. You can also just do the calculation at your own place. So now n, then there is 5n square, then there is 6n and 12. So we will increase the value of n from 1 to 10, then 100 and then 1000. N already is equal to 1. We have calculated this value. The 5n square takes 21% of the total CPU time when n is equal to 1. The 6n term takes 26% of the total time, and the 12 constant takes 52. So whenever we increase the value of n is equal to 10, okay, so whenever we increase the value of this equal to 10, at that very time, the 5n square will take 87.41 of the total time, because this is a square term. So n will be equal to how much? It will be equal to 100. 100 into 5, that will be 500. So it will be 500 divided by 5 plus 6 plus 12, okay? So at that very time, the value will come out to be 87%, because the quadratic term will go very much high. Accordingly, the 6n will be 6 into n is equal to 10, that's 60 divided by all the terms. Its percentage will come out to be 10. And the final term, that's 12, that will come to be 12 divided by the remaining terms, that will 2.09096, okay? Now, whenever we increase the value of n to 100, again, we will see the 5n square will become 100 into 100 into 5. So it will become a very big term, and to calculate that, to perform the computation of that big term will again need a lot of CPU time. And the 6n will need only this much of time in comparison to 5n square, and the 12 will need very much less time at that very time in comparison to other two terms. So accordingly, whenever we increase the value of 1000 n to 1000, the percentage time that 5n square in this function will take, that is equal to 99.88%. This is just, you can do it yourself. 6n will take only this much of time, and the 12 will take this much of time at that time. So from this graph, what we can conclude is that as soon as we increase the value of n from 1 to higher terms, 10, 100,000, the time, whole of the CPU time is taken by only this quadratic term. 99% and even more than that of the time is taken only by this quadratic term, while as linear term takes very less amount of CPU time, and constant time takes equal to 0. It takes in a very blink of the eye. So 5n square is equal to 99.88%. That is not exact, but that is approximately equal to 100%. There is only a minute gap between 100% and this 99.88. So if we can go for the approximate calculations, okay, we can say that this function f of n is equal to 5n square plus 6n plus 12. Since this 6n plus 12 takes only 0. Some percentage of CPU, okay, so we can eliminate those terms. Since near about 100% of the CPU time is taken only by this quadratic term, that is 5n square. So we can say fn will be equal to 5n square plus 6n plus 12. It will be equal to 5n square approximately, because the time which whole of this operation takes, that is only taken by this operation. The remaining they will just add up to the complexity. So better is to eliminate them. So eliminating these unnecessary terms, okay, eliminating these unnecessary terms from the expression and keeping only that term into the expression is how the asymptotic functions are actually deriving the complexity of an algorithm. So this is the same thing. Like normally till now, what we learned from this topic was that the complexity normally and majority of the cases depend on the size of the input parameter. Suppose if we are having a function or we are having an algorithm which is the addition of two matrices or the multiplication of two matrices A and B with m rows and n columns. This algorithm we also showed here on the PPT in the previous week. So its total complexity was dependent on the mn end. There was like something 2mn plus mn plus 1. It was the time complexity of addition of matrix addition. So the thing is that the total complexity of this algorithm was dependent on the input size, that is the number of rows in one matrices and the number of rows and columns in the other matrices. Similarly, if we want to find out the addition of a matrix of array whose elements are like 1 to 20, okay, so at that very time the size will be n will be 20, okay, the size will be, if n we will increase to 40, that is there are 40 elements inside this array. Again, the total time it will take will depend on the size. You know, normally what we are doing whenever we had to find time complexity of any algorithm, we implement it. Okay, we implement the algorithm like we did in the previous lab. You implement that algorithm. While you compute that algorithm, you see the total time this algorithm took. No doubt that is not the exact time complexity, but this is how we do. So the total time will be definitely depending on the size of that what you are computing, the size of the matrices, the other things like the size of the array. But there could be some scenarios, okay, where the size only is not the enough criteria upon which the complexity depends. Okay, कुछ ऐसे सिचुएशन है जहां पे खाली साइज पे ही ये डिपेंड नहीं होता है. लाइक द कॉम्प्लेक्सिटी इज नॉट डिपेंडेंट ओनली ऑन द साइज. फॉर एग्जांपल, अगर हम बात करें सर्चिंग एल्गोरिथम की, ओके, हमारे पास वी आर बीइंग गिवन एन एरे ऑफ साइज n, or we will take only it to size 20, and we are being given a number that is x is equal to 10, और हमें बताया जाता है that you have to search whether 10 is present inside this array of 20 elements. So what we do, जो पहला एलिमेंट है उस एरे का, दैट इज द एरे एलिमेंट नंबर 0, 0 लोकेशन पे जो एलिमेंट है, we will compare that element with our value which we are trying to find, and we will see whether a of 0 is equal to x. X is what we are finding. If it is equal to that, we return it. Otherwise, we increment and go to next location. This way, we will go from the element number 0, 1, 2, 3, 4, 5, 6 until we reach to the end of this array. When we reach to end of array, it means if it is a 20 element array, whenever we reach to a of 19, that will be the last element of this array. And if that last element will be the element which we are finding, it means we have to travel from each and every element of that array. So the complexity at that very time will be n. I will not use any big O or omega right now. It will be n because we have to travel each and every element of that array from 0 to n. And the final element is what we are searching for. But there could be another scenario, like whenever we compare this element which we are finding, that's x, whenever we do if x is equal to a of 0, जो पहला एलिमेंट है, अगर वही उसके बराबर है जो हमें चाहिए which we are searching, it means we don't have to traverse to each and every element of the array. जो पहला ही है वही हमें चाहिए, means only one unit of time. So there could be, in addition to the size of the element, there could be these scenarios. Okay, one more example is like we are doing sorting. Yes, sorting में हम क्या करते हैं, we start the first element, compare it with all the remaining elements and see whether it is, अगर ascending या descending में करना हो, whether it is lesser than that element, या whether it is bigger than the elements on the right side of that array. If it is bigger than that, we swap. छोटे को यहाँ लाते हैं, इसको उसकी जगह पे लाते हैं. So these swap operations take also the CPU time, that is the computing time. So now the case could be that the array which is being given to us, or the values which are being given to us, and you are being asked to sort these array, that values are already in sorted order. That is already like 2, 5, 10, 11, 12, 13, it is already sorted. But since you have to do the sorting, you don't know whether it is sorted or not. What you normally, the logic says, you will take the element, first element, compare it with all the remaining elements. If it is greater than the remaining n minus 1 elements, you will swap. If it is not, you will keep it like this, where it is. And you will increment I2 from 1 to 2, you will go to next element. Compare the next element with the remaining n minus 2 elements. Okay. So when it is already in sorted and you use the if condition, if this element is lesser than or bigger than the remaining all the elements, if the condition is false, then you swap. But if it is true, you don't swap. So this swapping time decreases. This time it takes for the CPU to swap the element number n, bring it to position number 0 and take the element number at 0 and take it to position number n. It will take some time. But since once the array is sorted itself, you don't need any swapping. So at that very time, the time complexity of the algorithm will be less in comparison to जब एक array आपको दी गई हो जिसमें सारे के सारे elements आपको one by one swap करने पड़ेंगे. Okay, these are the two examples, and based upon these two examples, there are three different kinds of step count: the best case, the average, and worst case. So by giving an example of these three cases, it will be clear what does the best case mean, average and worst. Like I gave the example of this search. So if an array is given and we are searching an element x, we compare it with the first value of array, that is a of 0. If that a of 0 is the element which we are searching, so we need only one computation, we need only one CPU cycle, we need only one program step, and so its complexity will be 1. At that very time, we say it is the best case. The first element gave what we are searching. The worst is when we are having an array and we compare our element with each and every element of the array, and our element is not found until we reach the end of this array. The last element is what we are searching for. This means we have to start from the first element, go for I plus plus, I plus plus, I plus plus until we reach to the end of the array. And the last element is what we are searching. This is the worst case scenario. And we use this terminology in our daily life also. The average case is like when the number is present something in the middle of the array. Neither it is present on the right extreme side of the array, nor it is present on the extreme left side. So it is somewhat in the middle, and average case is what we take on during those times. So this is again what I actually draw on the whiteboard. That's what is asymptotic analysis. Again, here a function, a general function an square plus bn plus c is given. So what does it say? That the quadratic term, that is the bigger term in the expression, actually dominates whole of the expression. The remaining terms, when the value of n gets increased, clear from this table, when the value of n gets increased from 110 to 1000, the highest term inside the expression actually takes much of the CPU. The remaining terms inside the expression takes CPU time equal to 0. So we eliminate those terms while we do the asymptotic analysis of the algorithm itself. And asymptotic का मतलब ही है which is approaching something like it takes initially this value. So when increasing it takes like this, moves more towards the fn side, जो हमने अभी white board पे graph draw किया है. So you can have a look on the last point. The simplest example is a function f of n is equal to n square plus 3n. The term 3n becomes insignificant compared to n square when n is very large. So the function fn is said to be asymptotically. Asymptotically का वही मतलब है जो approximately का है. जैसे हमने बोला उस प्रीवियस एग्जांपल में जहां टेबल हमने ड्रा किया कि the 5n square takes approximately 100% of the CPU time. No doubt it is not exact. There is some point something, because some little time will be taken by these terms. It won't be like they don't won't take, even if it is a fraction of millionth of second. But when we are not dealing with exactness, we deal with approximateness, and approximateness पे ही asymptotic analysis depend है. At that very time, we say that Fn is said to be asymptotically equivalent to n square as n tends to infinity. And written f of n is asymptotically dependent on n of square. और asymptotic notation से ही हमें पता चलता है the three program steps which we discussed, that is the best case, time complexity. We will only deal with time complexity. As I discussed it, that space is nowadays not an issue. The more of the focus is being given on the time. So to find out these three program steps, that is how this algorithm behaves in worst case, how its performance changes in the best case, and what is the average case performance of this algorithm. These three different program steps are given by these asymptotic analysis techniques. And the first of the asymptotic analysis technique is big O. There are three techniques for asymptotic analysis of an algorithm. The first one is big O notation. Then there is big omega notation, that's known as omega. And then there is the theta notation. These are the three ways of expressing the worst case, best case, and the average case performance of an algorithm. Again, these big O, theta, or omega, these asymptotic notations, these are a means to compute the time complexity of an algorithm. This is not something new. Only we take approximate analysis or calculation here. So if we have a look on the big O, what does it say? You see the big O, it is written as f of n is equal to big O g of n, means a function is given to us which is f of n, and we say if there is another function g of n, okay, and f of n is big O of that function, g and n, okay. F of n is a function, and its convention of writing is like this, and it is read as f of n, which is here in the brackets. This is how it is read as f of n is big O of g of n. This is the way how it has to be written, and this is what its formula says. And if any of our function f of n satisfies this formula, which means that function is big O of g of n. Like f of n, that its value should be greater than or equal to 0, but its value should be less than or equal to g of n multiplied by some constant c. And this condition should be true for every n which is greater than or equal to n0. It will come to it will get clear just after giving an example. So this function g of n, it is like it gives us the speed at which the function f of n gets increased. You know, initially we saw that there is a linear function, there is quadratic, and there is cubic, there is exponential. Whenever we increase the value of n in a linear expression, the corresponding f of n value also gets increased. But by which speed it gets increased? It gets increased equal to the speed of n. As we increase the value of n from 1 to 2 to 3, fn gets increased again. But when we go to quadratic, that's n square, the value of fn does not get increased linearly, but it gets quadratically. When n is equal to 1, fn is equal to 1. When fn is equal to 2, fn will get 4. So this shift, this increase in the value of fn, by how much value it gets increased, that is being given by this f of n. How much faster this algorithm grows or the complexity grows. And this, the value of gn which has been given, since it gives the value how much this fn value will get increased, so the function won't grow much more than that. This will be the upper bound, upper what we call limit. It won't grow much more than that. Just look at the example, you will get clear. See, we are having a function f of n, which is 5n square plus 4. And always, whenever you have to find its gn, that is another function. Because this is what big O says, fn and gn. These are two functions. Whenever you have to find big O of any function, it is given 5n square. Always take n square, तो रहेगा ही रहेगा. Okay? And जो इसका ये कोफिशिएंट है, उसका एक एक्स्ट्रा लीजिए, 5 + 1 6. क्योंकि यहाँ 5 अगर यहाँ 7 होगा, यहाँ पे 8 लेते हैं. ठीक है? So we will take gn is equal to 6n square because this is the highest term. This is what takes the maximum term in an asymptotic notation. So what we have to find is that whether fn is big O of gn. Can we say that if we write fn is equal to 5n square plus 4 and we write gn is equal to 6n square, can we say that fn is big O of g of n? So which means is g of n, जो g of n फंक्शन है, is it the least upper bound on f of n? कि n स्क्वायर से ऊपर ये ग्रो नहीं कर सकती. It won't grow cubically, it won't go exponentially. The least it can grow is quadratically. Yes. So from the definition of whether function is big O of gn, we know it should satisfy this condition. Fn should be less than or equal to c of gn. This is what big O is all about. Fn is less than or equal to c of gn. So let's put c is equal to 6, because this we will get clear only when we see the value of this function. It is 5. Let's put it c equal to 6 and we will see. So 5n square plus 4 should be then less than or equal to 6n square, because fn is 5n square plus 4. Less than or equal to is already there in the formula. C in place of c we put 6 and gn is again equal to n square. So we will see whether this inequality sign or inequality will get satisfied. So whenever we say 5n square plus 4 should be less than or equal to 6n square, which means that n square should be greater than or equal to 4. Okay, you can put here values like n is equal to 1, n is equal to 2. You will see this condition will be satisfied only when we put n square's value greater than or equal to 4. This is what it means. It's not like I have written it like this. You can put value and you will see this condition should be there. So it means n square's value should be greater than or equal to 4, which means the value of n should be greater than or equal to 2. And this is what from the definition when we say the n should be greater than or equal to some value n0. Some value n0 is 2 in this example. Here, this n should be greater than or equal to this 2 is equal to n0. You getting? So this condition 5n square plus 4 is always less than or equal to some constant into n square. This is true only when the value of n is greater than or equal to 2, first condition, and the value of c is equal to 6. It will be always true. Okay, so we can say yes, so fn is c of gn for all n greater than or equal to 2, and c is equal to c is equal to 6 and n0 is equal to 2. So whenever you put this becomes an upper limit. This becomes the upper limit as a big O notation for this function. So you can say it that the big O will eliminate all those terms. The 5n square plus 4, the 4 will be eliminated here and the function will be dependent only on n square. Okay, because this is what it will be. It will take the most of the time, and that is what the asymptotic analysis gives. You just have a look on the example. We are having a program. The purpose of the program is to compute sum of the n elements. You are being given elements from 1 to 20, means 1 to n. और आपको बताया जाता है कि सारों का हमें सम करके दीजिए. So suppose this person came and he developed this algorithm. He declared int 1 I sum में पहले 0 इनिशियलाइज और n. फिर यूजर से लेता है कि n कितने एलिमेंट्स का आपने सम करना है. उसके बाद लूप चलाता है फॉर i इज इक्वल टू i लेस देन n i प्लस प्लस कि जितना एलिमेंट इसको सम कराने हैं वहां तक लूप ये चलाएगा और सम में अकॉर्डिंगली इंक्रीमेंट करता जाएगा प्रीवियस वैल्यू और न्यू वैल्यू, प्रीवियस वैल्यू और न्यू वैल्यू. उसके बाद ही विल printf the sum function. Now we see whenever we discussed it throughout this class that the assignment operator is always a CPU consuming operator and it will take one time. So if I have written on the right side of this instruction, it will take one execution. The scanf, you have to take one value from n and store it somewhere. And n itself means that you are assigning it to some memory, which means one time. So the for loop, the assignment operator, that is sum is equal to sum plus 1. It will be executed n number of times depending upon the total number of numbers you want to add up. Then the printf, you will print some value of sum one time, return one time. So if I write it as a function, the result of this algorithm, that is the time complexity, it will be f of n is equal to n plus 4. N is one time and one time is 4 times. That is n plus 4. Now, since it is linear, it means its upper bound will be also linear. And we have to actually find its asymptotic, and that asymptotic means we have to erase all the constant and the little term. So the 4, by looking just at this example, we will see the 4 will be erased. But how it has to be done using the actual definition is we have to find whether g of n is equal to n. Okay, means f of n is big O of g and n. This is what we have to find. So from the definition, this means f of n should be less than or equal to c of gn. F of n again is n plus 4 in this case. That is the time complexity of this program which we wrote here. It means n of n plus 4 should be less than or equal to c into n. Again, take c is equal to 2. As I said, जो इस variable का left hand side में होगा उसका एक extra. So here it is 1. So we will take it c is equal to 2. Okay. So this will become n plus 4 is less than or equal to, in place of c it is 2 and in place of n it will be like n. So to make this inequality true, that's n plus 4 should be less than or equal to 2n. That means n should be greater than or equal to 4. Why? Because if we put n is equal to 1 here, it will be 4 plus 1, that will be 4. Less than or equal to 2 into n के बदले आएगा 1, that is 2. But that is not less than, that is greater than. So it will be true only when we put n greater than or equal to 4. और वही n हमारा n0 का वैल्यू बन जाएगा. So n0, c will be 2, n0 will be 4. The actual big O notation is to find the values of the c and n0. That's what big O is all about. बाकी आपको पता चलेगा यहाँ से ही कि ये जो है फंक्शन ये कौन से टाइम में ग्रो करेगी, whether it will grow maximum in linear, quadratic, that you will get clear only from this thing. So yes, we can say the function f of n is big O of n because n is the upper bound in which it can grow. It won't grow to n square, it won't go to n cube. Since it is linear, it could go only linear, and majority of the time will be taken by the n parameter. Because when n is equal to 1 crore, fn is equal to 1 crore plus 4. तो 1 करोड़ को आप 4 से डिक्रीज करो या कम करो, वो दैट विल बी इक्वल टू 1 करोड़. क्योंकि यहाँ पे हम इनफिनिटी की बात करते हैं, जब हम एसिम्प्टोटिक की बात करते हैं तो यू ऐड समथिंग टू इनफिनिटी और डिक्रीमेंट, इट इज वन एंड द सेम थिंग. सो यस, वी से दैट fn इज इक्वल टू बिग O ऑफ n. नाउ this is the program to add numbers from 1 to n using a for loop. Yes, this my brother used this algorithm to solve it, but I will ask now you to design another approach of solving the same problem. So what you will do, you will say, suppose we will declare the main function, we will declare I sum and everything, then we take the value from the user n, and what we do, we just go printf %d n into n plus 1, but that is the Euler's formula. You know Euler's formula, this is n into n plus 1 by 2. If you don't know, I can write it here. Yes? Yes, we can have this discussion. It's like, for example, we are giving numbers n is equal to 10. So it means 1 plus 2 plus 3 plus 4 plus 5 plus ऐसे कर करके 10 तक हमें सम करना है. तो जब हम इसको ऐड करेंगे it would be 55. And this is what my brother actually implemented. पहले 1 को लिया, उसको 2 के साथ, 3 के साथ, 4 के साथ ऐसे करके जो n is equal to 10. But there is another, it is known as Euler's formula. यूलर्स फार्मूला बोलता है कि अगर आपको n एलिमेंट्स का सम बोला है करने के लिए, और यहाँ पे चूंकि n हमने 10 एलिमेंट का लिया, तो आप फार्मूला यूज कर दीजिए डायरेक्ट n into n plus 1 divided by 2. So चूंकि here I have been asked to find the sum of the 10 elements, so it will be 10 into 10 plus 1 divided by 2 according to formula. So this will be 5. It will be 5 into 11. That will be 50. And this is not only in this case, this is true every time. This is a shortcut way to do the summation using mathematical techniques. And that is what we are doing here. We take the value from the user and just use this formula to compute the sum and give it to the user. So this will be executed one time. This will be executed one time. This will be executed one time, because we don't start from 1, then increment to 2, 3, 4, 5, 6. We just take the last value 10, use the arithmetic operation and find the total. Then we will return that statement. So to find the total complexity of this algorithm, complexity means time. Fn will be equal to 1 plus 1 plus, that is 4. So it will take 4 units of time. And this one was taking how much? It was taking n plus 4 units of time based upon the value of n. So now gn is equal to 1, which means we have to find that it will grow constantly. Yes, is gfn is equal to function of big O of g of n, which means fn should be less than or equal to c into gn, which means we have to find the value of c and the value of n0 according to definition. From fn 4, we will put 4 here, less than or equal to c into gn. Gn we are taking as 1. Okay, and since it is 4, so you can take c is equal to 5. So 4 less than or equal to 5 into 1. So it means c should be greater than 5. Okay, and n0 should be equal to 1. If you want to satisfy this function, that is fn should be always less than or equal to c into gn. So if this condition holds true, the value should be like this, and we can say at that time that the function f of n, that is big O of 1. Big O 1 means this one, okay, g of n 1, और big O का चूंकि definition के हिसाब से इसको satisfy करता है. And yes, if we don't go to the definition part, we can also directly say from here, whenever you are giving a function f of n is equal to 4, it means it is a constant time, it is a constant term. You will always keep in mind that it will take big O of 1 time. If it is linear, big O of n. If it is quadratic, big O of n square, and according to the same. I think this is enough for today, huh? Because it will keep on getting increased. We are having still in this week. We will clear this all those lectures of like chapter 1, and then we will shift to another one.